Alright, so today I'm going to be talking about big O notation. So a lot of times in computer science, it's very helpful to try and reason about an algorithm, particularly in terms of its performance. So the way that computer scientists do this is with big O notation. Um, a lot of times an algorithm, for example, the bubble sort that we looked at last class, will perform on some input and its performance will be dependent on the size of this input. So we usually reason about this by saying that the size of the input is this variable called n, and then trying to talk about how long it's going to take with respect to that size. So we do this by using this big O to represent the worst possible runtime, and the big omega to represent the best possible runtime of our algorithm. So what this is trying to say is that given an array, for example, if we're talking about bubble sort, given an array of size n, what is the best amount of time that bubble sort will take, and what is the worst amount of time that bubble sort will take? Or what is the fastest that it can sort the array, and what is the slowest possible time that it can sort the array? So if we remember from last class, the way that bubble sort worked is that it compared pairs of integers in the array at a time, bubbling up the largest to the right side of the array, and then continuing until the entire array was sorted. So if we try and reason about the best possible case for bubble sort, I would argue that the best possible case would be an array like the following. Given an array of integers that is already pre-sorted, bubble sort will simply walk through comparing two at a time and then exit after it realizes that the entire array is sorted. In this case, it does not need to swap any of the integers. All that's needed is the comparisons at each step, and so this runs in n time, where n is the size of the array. So like it'd be order some constant times 5. So this gives us our big omega for bubble sort. If we try and talk about the worst possible case for bubble sort, I would argue that the following array is the worst case for bubble sort. In this case, each pair needs to be swapped. For example, 5 needs to be swapped with 4, then with 3, then with 2, then with 1. Then 4 needs to be swapped with 3, then 2, then 1. 3 needs to be swapped with 2 and 1. 2 needs to be swapped with 1. So that is a total of 4 plus 3 plus 2 plus 1 swaps, which is 10 swaps. So if we think about how many swaps there need to be, it's really a sum from 1 to n minus 1, where n is the size of the array, if it's a reverse sorted array. And so we can reason about this, and applying the formula for the sum of an arithmetic sequence, we can see that the worst possible runtime for this algorithm is actually n squared. So I'm just going to write that down.